Inside a sealed container, a pure liquid is never truly at rest. At the surface boundary, molecules gather enough kinetic energy to break their intermolecular bonds and escape into the space above. These gaseous molecules continually collide with the liquid surface and re-enter it. When the rate of escape equals the rate of return, the system reaches equilibrium, exerting a constant, measurable force known as vapor pressure. Introduce a second liquid into that closed system, and the internal environment immediately changes. The native molecules are now forced to interact with foreign particles. To utilize this mixture, we have to determine whether the two substances will blend into a highly predictable solution, or if their opposing forces will create erratic physical behavior. Measuring these intermolecular interactions allows us to mathematically derive the absolute properties of the molecules themselves. Predicting how these mixtures will evaporate, boil, or freeze requires an analysis of two specific factors: the microscopic symmetry of the intermolecular forces and the absolute quantity of particles present. We begin with a mathematical baseline, the ideal solution. This is a mixture that perfectly obeys Raoult's law, scaling its vapor pressure predictably across every possible concentration. This strict obedience requires absolute energetic symmetry. As shown in this model, the attractive force between two molecules of substance A, the force between two molecules of substance B, and the new bond between A and B must be mathematically identical. The molecules experience no energetic difference between their own kind and the foreign substance. They move and interact as if they were still a pure liquid. Because no new energy states are created or destroyed by this mixing, the enthalpy of mixing is zero. The system neither absorbs heat nor releases it. Furthermore, the mixed molecules fit into the same spatial arrangement as they did independently. The total volume is simply the sum of its parts, meaning the volume of mixing is also zero. Perfect symmetry is rare in physical chemistry, but this ideal state provides the exact mathematical framework required to track the chaotic deviations of real-world liquids. This graph maps vapor pressure against the mole fraction of a mixture. The straight diagonal line represents Raoult's law, our ideal baseline. When liquids with mismatched intermolecular forces combine, the measured pressure curves away from this theoretical path. If the new interactions between the mixed molecules are weaker than their pure states, the molecules repel each other slightly. They escape into the vapor phase at a much higher rate than predicted, driving the curve upward in a positive deviation. If the mixed molecules form stronger bonds with each other than they did alone, they trap one another inside the liquid state. Vapor pressure drops below the ideal prediction, creating a negative deviation. At extreme points of deviation, these chemical mixtures lock into a highly restrictive state, known as an azeotrope. At a precise concentration, an azeotropic mixture will boil at a constant temperature. The vapor taking flight possesses the exact same molecular composition as the liquid left behind. Positive deviations generate minimum boiling azeotropes, which boil much earlier than their pure components. Negative deviations lock the molecules tightly together, forming maximum boiling azeotropes that demand intense heat. Because the boiling liquid and the resulting vapor share an identical ratio of components, standard physical separation techniques fail. An azeotrope cannot be divided by simple distillation. We can manipulate the thermodynamics further by restricting the system entirely. We do this by dissolving a completely non-volatile solute into the liquid, a substance incapable of turning into vapor. Once introduced, the chemical identity of this solute becomes irrelevant. The system is now driven by colligative properties, which respond strictly to the absolute number of solute particles present in the solution. Look at the fluid mechanics at the surface. The inert solute particles physically occupy surface area. They act as a mechanical blockade, actively preventing solvent molecules from crossing the boundary into the vapor phase. This physical crowding directly suppresses the vapor pressure. The exact relative drop in pressure is mathematically equal to the mole fraction of the introduced solute. For highly dilute solutions, we simplify this relationship. We can connect the drop in vapor pressure directly to the measurable mass and molar mass of both the solvent and the solute. This surface-level blockade forces the thermal boundaries of the liquid state to expand, shifting the specific points where the substance is capable of transitioning into a gas or a solid. This phase diagram charts temperature against pressure. A liquid can only transition into a boil when its internal vapor pressure climbs high enough to intersect the atmospheric pressure line at the top. Because the non-volatile solute artificially suppresses the vapor pressure, the liquid needs significantly more thermal energy to force that intersection. The boiling point is elevated. At the cold extreme, these same inert particles mechanically obstruct the solvent from organizing into a rigid crystal lattice. The system must draw out even more heat to force a freeze, depressing the freezing point. Both of these extreme boundary shifts are governed by parallel colligative equations. The shift is calculated by multiplying a unique thermodynamic constant for the solvent by the molality, a strict measure of the concentration of the obstructing particles. This particle-driven crowding forces structural shifts to the boundaries of the liquid state itself, redefining when a substance remains a fluid. We transition these thermodynamic laws from theoretical physics directly into applied laboratory analysis. Suppose we dissolve 1.80 grams of an entirely unknown solid into 90 grams of pure benzene. Upon heating the solution, we measure a strict boiling point elevation of 0.88 Kelvin. We insert that 0.88 Kelvin shift directly into our colligative equation, pairing it with benzene's known ebullioscopic constant. By isolating the single unknown variable, the math resolves to exactly 58 grams per mole. We have deduced the molar mass of a complete mystery compound entirely by measuring how hard it is to boil a liquid. Calculating these specific phase manipulations allows engineers to design robust industrial coolants, scale up chemical distillation towers, and verify the precise purity of pharmaceutical compounds. Whether isolating azeotropes or exploiting colligative constraints, true control over physical chemistry relies on a single principle. The macroscopic behavior of matter is completely subordinate to the microscopic symmetry and statistics of its particles.